Good evening, everyone. My name is Jessica Gardner, and as the University Librarian here at Cambridge, it's a great pleasure that it's my job to introduce the Sandars reader for 2017-18, Dr. Peter Wothers. Just a tiny bit of housekeeping. The mic here isn't on, so can I just check that you can hear me sufficiently? Fantastic. Peter is mic'd up, so you can hear me. Dr. Peter Wothers is a teaching fellow in the Department of Chemistry and a fellow and director of studies in chemistry at St Catherine's College. Dr. Wothers has been an inspiration, both for those of us who've been for the lectures the past two nights, and of course all those he's taught and whose lives he's touched during his time as a lecturer and teacher. In his first lecture, The Spark, he introduced his interest and passion for his book collecting and his addiction to the history of collecting chemistry books. And his second lecture yesterday on the hydrogen crystals of dawn gave an insight to how those chemical experiments had changed over time and how they were seen through the lens of his collection. It's a real delight to have so many of you back who've been to the first lecture, the second lecture, and here for its conclusion. But for those of you who are new this evening, I'll also give you a little bit of background about Peter and about Sandars' lectures particularly. Dr. Wothers began his first lecture explaining how from a young age he had begun to collect antique books. He called it an addiction, and that's what we saw on the first night. With great passion and joy, he showed us what he'd achieved through 30 years of collecting, ending up with over 1,000 historical chemistry titles in his personal collection. 1,000 so far, anyway. After the lecture, there will be the opportunity to see treasures from that collection here tonight, and also to join us for a glass of wine and to ask further questions after the lecture. Now, I should also explain that Dr. Wothers is an author in his own right and has contributed widely to public understanding of science in general and to chemistry in particular. He has co-authored a number of popular undergraduate textbooks, including Why Chemical Reactions Happen, Chemical Structure and Reactivity, that one with his colleague James Keeler, who is with us in the audience today, I believe. It's a joy to have him here as well. And also a book on organic chemistry. Now, you will see that Dr. Wothers is a fantastic public speaker on science, and so it will be no surprise to any of us that he's made a number of TV and radio appearances, including presenting the Royal Institution Christmas Lectures, The Modern Alchemist, on BBC Two in 2012. Peter Wothers has also been involved in the national and international chemistry Olympiad competitions and has initiated the successful Cambridge Chemistry Challenge, supported by his college here at St Catherine's. Dr. Wothers has also just completed a new book looking at the history of chemistry through the names of elements, and this will be launched early next year. He was in 2014, for reasons you will understand, most deservedly awarded an MBE for services to chemistry. Now, the Sandars lectures themselves began in 1895 with a bequest from Samuel Sandars, a 19th century barrister, a great bibliophile, and a fellow of Trinity College. He left what would have seemed a very grand sum of £2,000 in that time, and that has accrued and enabled the endowment over that time of readership in bibliography and paleography to the University Library, and contributed through that to the scholarship at many Cambridge institutions. He stipulated there should be one or more lectures, and we've ended up with three, as part of our package, on bibliography, paleography, typography, bookbinding, and so on, or the science of books and manuscripts, or the science is what we are emphasising in these lectures. And he desired for those to be, as far as possible, illustrating what was held in collections here at Cambridge. In this occasion, a private collection. In other occasions, they draw on the great collections of the University Library and other college libraries around our institutions. Now, as well as Sanders' generous gift to crown the lecture series, he also gifted many of his own early English printed books and illuminated manuscripts to Cambridge libraries. And in this way, his gift in the 19th century continues today to enhance collections and scholarship for all current and future generations here at Cambridge. And I'm really proud to say, as the Cambridge University Librarian, that the Sandars bequest has resulted in one of the major British bibliographical lecture series, the Sandars Lectures, being here at Cambridge, continuing since 1895 with a very proud tradition, except for a brief suspension during the two Great Wars. Those have been held annually, and Dr. Wothers is the 110th Sandars lecturer to accept the invitation. We're very, very glad that he did. Throughout the lectures this week, Dr. Wothers has taken as his theme chemical attractions. This evening is the final and concluding lecture, and it's called Women's and Children's Firsts, and the title and the substance chosen most aptly to celebrate International Women's Day. We're really glad to mark that here in St Catherine's College. And it's therefore with great pleasure that I present to you the final Sandars lecture of 2017-18, Dr. Peter Wothers.
Thank you. Well, thank you very much. But actually, before I begin today, I have unfinished business, okay? So for those of you that were here yesterday, you know that we had a failure in one of our experiments, okay? And I can't leave it like that. We've rewired everything, so hopefully it's going to work today. So this was to illustrate, for those of you that were here yesterday, you saw in the exhibit outside afterwards a fantastic 18th century pistol that is fired by simply a drop of ether to provide this explosive mix. And this is what we're trying to recreate. I put my glasses on. Right. So I'm hoping it's all going to work this time. So I just need to make that on. Okay, good. Right. So now the discoverer of this, so this was the Dutch chemist Jan Ingenhousz. He said that he is very temperamental, that you need to get just the right amount of ether. And he said, 2 drops and that's it. And we were experimenting with this in the lab, and it really was the case that actually it needs to be 2 drops. So hopefully this is going to be enough. I think I've put 2 drops in there. It's quite difficult to see in the light, but there we go. Now, he used static electricity from a Leyden jar to create the spark. We've got some modern technology that failed us yesterday, but hopefully it's going to work today. So hopefully this will work. Well, let's give it a try. So 3, 2, 1. Oh, phew. Good. And no damage to the fabulous McGrath, thank goodness. Our bursar will be relieved. Okay, thank you. So, of course, it's my pleasure to be here today to give this 3rd Sandars lecture for 2018. And as I'm sure you've realised, in fact, as you've heard, today is International Women's Day, and it's no coincidence, of course, that I've decided to give this final talk on early chemistry books written by women. Some of these, as we shall see, were also written for younger students of both sexes. But the first book I wanted to bring to your attention is a little book entitled La Chimie charitable et facile en faveur des dames. There's something like that, if you'll excuse my French. The first edition is dated 1666, but sadly I only have a copy of the 3rd edition from 1687. Much of the material that I shall be presenting here for this section, by the way, including translations from the text, is from the excellent article by Lucia Tosi published in Ambix in 2001. In the first edition, the author's name appears as Damoiselle M.M. Her name is given in the 3rd edition, but not on the title page, instead at the end of the dedication page. In this 3rd edition from 1687, the publisher states that the damoiselle who composed the book was one of the most brilliant minds that had appeared in his time. Her sudden death, however, had deprived him of other treatises that she had promised and which could not be found. All that he could do was to recover the copy, revised and extended with several new and curious preparations which had been added to the 3rd edition. In the preface to the first edition, the author writes, "When I began this small treatise, it was for my sole satisfaction, so as not to lose memory of the knowledge that I had acquired by means of long toil and by diverse experiments repeated several times. I cannot conceal that seeing it achieved beyond what I had dared to expect, I was tempted to publish it. But if I had reason to bring it to light, I had even more reason to keep it hidden, and not to expose it to general censure. I dwelt irresolute in this combat almost 2 years. I objected to myself that teaching was not the profession of a woman, that she ought to remain in silence, to listen and to learn without bearing witness that she knows, that it is above her to give a work to the public, and that such a reputation is not by any means advantageous. I prided myself that I am not the first woman to have placed something under the press, that mind has no sex, and if the minds of women were cultivated like those of men, and if we employed as much time and money in their instruction, they could become their equal. Well, Muriaticum had her own laboratory and made her preparations herself, many of which she freely gave away to the poor. And she also encouraged other ladies to perform experiments. For those ladies who are content to know without desiring to make the effort to perform the operations which they judge to be necessary because of the time required or the different sort of vessels or of the other utensils which are needed, or who fear not to succeed, I shall personally explain whenever one makes the honour to tell me, and I shall take care to perform myself whatever one may want me to teach. Well, Lucia Tosi, in her paper, notes many similarities to the Traité de la Chimie of Christopher Glaser, but actually his work in turn shows many similarities to the work of Began that we discussed earlier in the week. Muriaticum begins with a discussion of the Paracelsian principles salt, sulphur and mercury into which matter can be resolved, and then discusses the operations of chemistry in a manner very similar to Began. She then discusses the vessels used, and then a section on lutes. These are the mixtures used to try to form a seal between two different vessels. Muriaticum recommends a mix of clay, egg white, butter, iron filings, sand, and a little urine thrown in for good mix. This is slightly different from the recipe used by Glaser, who added his secret ingredient of well-cleansed and sifted horse dung. After lutes, Muriaticum then talks of the different furnaces used and the symbols, this is what we see here, used in chemistry, and finally the weights and measures used. In short, everything needed to begin performing your own chemical operations. Section 2 of the book is devoted to vegetables and looks at preparations, mainly distillations, of tinctures, waters and essences. The third part looks at preparations from animal materials, including the essence of man's skull, a rather gruesome preparation then in vogue. For example, in Glaser's work, he writes, "Take the skull of a man dead of a violent death, cut it into such little pieces as may enter into a glass retort, of which leave the third part empty, place the retort in an earthen dish in a sand furnace, and fit thereto a great receiver, well luted, that the spirits may not be lost, and when the lute is dry, give fire gradually. There comes over a little phlegm at first, and after a spirit, which will fill the receiver with a white mist. At the time, you must govern your fire discreetly, otherwise the spirits pressed too hard will force the joints or break the receiver." He goes on, but we needn't continue with the gory details there. But just in case you were wondering what this recipe is for, he tells us that the salt of man's skulls is peculiarly proper for falling and mother fits. I have no idea what mother fits are, but there we go. Well, the fourth part of Muriaticum's book, though, deals with preparations from metals and minerals, whilst the fifth deals with compositions for health, medicines proper. The sixth and final part of the work deals with cosmetics, including giving advice on the treatment needed for different types of skin, and she recommends avoiding the compounds of mercury and bismuth then in fashion for whitening the skin. All in all, this little book is a marvellous publication, and I hope I can find the other editions. The next work I wanted to mention, and again we're only just going to touch on this, this is absolutely brilliant mind and a leading intellectual of the 18th century, but since she was more of a physicist and mathematician, she doesn't totally qualify for today's talk. Besides, many papers and books have also been written about her life, and this is Emily de Chatelet, who was born in 1706 and who tragically died in 1749 during childbirth. She is best known for her Institution de Physique, published in 1740, and her translation and commentary on Isaac Newton's Physics, Principia. Also of historical interest, of course, is the great love affair between her and Voltaire. However, today we are concerned with her work on fire. This book was her entry into a competition on the nature of fire. Her lover, Voltaire, had decided to enter, and Chatelet, after realising that she did not really agree with his approach, decided also to enter, but in secret, without telling Voltaire. Whilst he spent a fortune buying expensive equipment and running experiments trying to measure the weight of heat, she had to work in secret with no apparatus. Her entry was submitted in September 1737, and the results were announced on April the 16th the following year. Neither she nor Voltaire had won. Instead, the prize went to the mathematician Euler. However, Voltaire arranged for both their works to be published together with the winner and the other two authors who were ranked second. But one thing that's really nice in this book is she suggests an experiment that she would love to try, but she can't because she's doing all this in secret without Voltaire knowing. She wants to split up light into the spectrum against the wall, just as Newton had done before, but put thermometers there so she could see if the temperatures were different. And that's a nice experiment, and somebody did that later, a man, unfortunately, but we'll come back to it a bit later in the lecture. So I'm also afraid that we're going to have to rush through the next chemist as well. This is because I want to get to somebody later. And the next one, though, is Elizabeth Fulham, about whom very little is known, apart from the fact that she published a most interesting series of chemical experiments. These were all about trying to successfully dye cloths with gold or silver. She writes, "I first imagined that the proper title of this performance should be An Essay on the Art of Making Cloths of Gold, Silver and Other Metals by Chemical Processes. But reflecting on the imperfect state of the art, and that my experiments related not only to the reduction but also to the calcination of metals and other combustible bodies, I determined to entitle it An Essay on Combustion with a View to the New Art of Dyeing and Painting, which includes everything the experiments can extend to." I have first editions from both, well, only editions from both the English from 1794 and the American edition from 1810. And she states that in the work she will endeavour to show that the hydrogen of water is the only substance that actually restores oxygenated bodies to their combustible state, and that water is the only source of oxygen which oxygenates combustible bodies. So what this means, for example, is she thought that during the reduction of a metal oxide by charcoal, as happens during the smelting of metals, the carbon is actually oxidized by the oxygen in the water, and it's the hydrogen formed from this that's released there that extracts the oxygen from the mineral ore, reforming the water but liberating the metal. It's an ingenious theory, and she had some evidence at the time to back it up, but sadly it did not stand up to stricter scrutiny as better techniques became available. Fulham also accepts the French nomenclature and hence the theories of Lavoisier, about whom we heard yesterday. She writes, "I have adopted the French nomenclature as the terms of it are so framed as to prevent circumlocution, assist the memory by pointing out the combination and state of the elements exist in each compound as far as they are known. Advantages to be found in no other nomenclature." But she also notes, "However, the English reader must regret that the French chemists have not preferred the terms air and ammonia to the less harmonious sounds gas and ammoniac. I took the liberty of writing the latter ammonia." Well, sadly, we're going to have to leave Mrs. Fulham now in order to get to our main topic for tonight, and this is Jane Marsay. I must admit, this is one that I've known about for many, many, many years. This is one of the ones that I came across in John Reed's Humour and Humours in Chemistry that we learnt of in the first lecture. but I'm sad, embarrassed to say that it was only relatively recently on speaking to an authority, an expert who's sitting at the back there, and it's very slightly embarrassing speaking in front of him. But anyway, so this is Frank James from the Royal Institution. He corrected me, of course, and said that, well, she was Swiss, and so obviously it's Marseille. So thank you for that. But anyway, so Jane Marseille was born Jane Hallimond in 1769, and she was one of 12 children and the only surviving daughter of a wealthy Swiss merchant, Anthony Francis Hallimond, who resided in London. When she was 15 years old, her mother died, and she found herself at the head of the household, having to look after her many siblings. She married Alexander Marseille, a native of Geneva, who was a physician and taught at Guy's Hospital in London. He was more interested in his chemical pursuits, and he gave up his position at the hospital on the death of Jane's father, when the inheritance made them financially secure. But she is particularly known for her Conversations series of books for children, notably her Conversations on Chemistry. And this was first published in 1806, and it went through many editions. And these are the different editions. Curiously, there seems to be no 7th edition, which I haven't quite worked out that one. I don't know if Frank knows anything about this, he can tell me later. But apparently there wasn't a 7th edition, but there we go. I've managed to acquire a few of these, but I'm most disappointed that I missed out on a copy of the first that came available at one point. By the time I'd phoned up the dealer, it had gone. I do have a copy of the first American edition from the same year, but I really look forward to finding the one from London eventually. The preface, more of which later, remains virtually unchanged from the first to the last editions, and it begins with an apology. It states, "In venturing to offer to the public, and more particularly to the female sex, an introduction to chemistry, the author, herself a woman, conceives that some explanation may be required, and she feels it the more necessary to apologise for the present undertaking, as her knowledge of the subject is but recent, and as she can have no real claims to the title of chemist." Well, whilst Jane did not have a claim to the title of chemist, her husband, Alexander, certainly did. He was born in Geneva, but studied medicine at the University of Edinburgh under the master chemist Joseph Black, who we heard about yesterday. After graduating, he moved to London, where he worked for a while as an intern at charitable dispensaries before practicing medicine and teaching chemistry to medical students at Guy's Hospital. Jane and Alexander married in 1799, and some of his personal notebooks still exist, and these shed light on the genesis of Conversations, as we shall see in a bit. But first, what inspired Mrs. Marset to write in the form of Conversations? Well, these were quite popular at the time, and another woman, Priscilla Wakefield, had already had a long career as an author. Her scientific books were more biological than chemical. For example, Domestic Recreation or Dialogues Illustrative of Natural and Scientific Subjects, which appeared in 1805, had chapters on insects, sea anemones, meteors, the human eye compared with those of animals, and the natural history of the cuckoo. However, the book took the form of dialogues between a Mrs. Dimsdale and her daughters, Lucy and Emily. Now, in the preface to one of her other books, Jane Marset, this is her book, Conversations on Political Economy, she justifies the style, saying, "The questions gave the author an opportunity of introducing objections and placing in various points of view questions and answers as they had actually occurred in her own mind." So this is why she chose them. And in fact, Jane had already written an elementary text on physics in the form of a dialogue for her young sister Sarah. And at the end of the preface to her first published work, Conversations in Chemistry, she reveals that this was not actually intended to be her first publication. At the end of the first edition, she writes, "It will be observed that from the beginning of the work, it is taken for granted that the reader has previously acquired some slight knowledge of natural philosophy, a circumstance indeed which appears very desirable. The author's original intention was to commence this work by a small tract explaining, on a plan analogous to this, the most essential rudiments of that science. This idea she has abandoned, but the manuscript was ready and might perhaps have been printed at some future period had not an elementary work of a similar description under the title Scientific Dialogues been lately pointed out to her, which, on a rapid perusal, she thought very ingenious and well calculated to answer its intended object. Well, this book, or books as I should say, since 6 volumes in the series eventually appeared, were written by Jeremiah Joyce, going through numerous editions, first published in 1800. I'm afraid my own copy of volume 1 of the first edition looks like it had a bit of an accident in one of the scientific experiments it describes. However, since the English short title catalogue lists only Birmingham as having a copy, plus 2 in the States, I think it's nice to have even this one. However, by the time of the 6th edition, Marseille had modified her preface slightly, and she writes, "This idea that she has since abandoned, an elementary work on natural philosophy having appeared just as the first edition of Conversations on Chemistry were preparing for the press. Her intended tract, however, was actually written, and subsequent considerations have lately induced her to offer it to the public." This was modified once again in the next edition, the 8th, and then remains unchanged in subsequent editions. Here she writes, "The reader will perceive, in pursuing this work, that he is supposed to have previously acquired some slight knowledge of natural philosophy, a circumstance so desirable that the author has, since the original publication of this work, been induced to offer to the public a small tract entitled Conversations on Natural Philosophy, in which the most essential rudiments of that science are familiarly explained." In the preface to Conversations on Natural Philosophy, which appeared in 1819, she states, "They are intended in the course of elementary science to precede the Conversations on Chemistry, and were actually written previous to either of her former publications." Interestingly, Jeremiah Joyce published his own Dialogues in Chemistry in 1807. This book features the tutor with students Charles and James. In the preface to this he states, "No person in connection with chemical reading ought to omit an opportunity, if it presents itself, of attending a course of lectures which always include a variety of illustrative and instructive experiments. Those indeed will esteem themselves highly fortunate who have and who embrace the opportunity of attending Mr. Davies' analytical course. It is, however, absolutely necessary before such can acquire any real advantage, even from these lectures, that they should be completely acquainted with the terms and phrases made use of, or they cannot follow, for any space of time, however small, the reasoning of the learned professor. To enable young persons and others to attend lectures with advantage, these volumes are laid before the public, with confidence that they cannot fail to answer the end designed." Well, there we go. Davies' lectures at the Royal Institution were extremely popular at the time, with many ladies and gentlemen eager to attend. And actually we have a syllabus of this on display outside for you to see later. But it seems that Jane Marseille had encountered exactly the same problem noted by Joyce, as she explains in her preface. She says, "On attending for the first time experimental lectures, the author found it almost impossible to derive any clear or satisfactory information from the rapid demonstrations which are usually and perhaps necessarily crowded into popular courses of this kind. But frequent opportunities having afterwards occurred of conversing with a friend on the subject of chemistry and of repeating a variety of experiments, she became better acquainted with the principles of that science and began to feel highly interested in its pursuit. It was then that she perceived, in attending the excellent lectures delivered at the Royal Institution by the present Professor of Chemistry, the great advantage which her previous knowledge of the subject, slight as it was, gave her over others who had not enjoyed the same means of private instruction. Every fact or experiment attracted her attention and served to explain some theory to which she was not a total stranger. She had the gratification to find that the numerous and elegant illustrations for which that school is so much distinguished seldom failed to produce on her mind the effect for which they were intended. Hence, it was natural to infer that familiar conversation was, in studies of this kind, a most useful auxiliary source of information, and more especially to the female sex, whose education is seldom calculated to prepare their minds for abstract ideas or scientific language. As, however, there are but few women who have access to this mode of instruction, and as the author was not acquainted with any book that could prove a substitute for it, she thought that it might be useful for beginners, as well as satisfactory to herself, to trace the steps by which she had acquired her little stock of chemical knowledge and to record in the form of dialogue those ideas which she had first derived from conversation. Now, Marseille has to apologise for just how bright her two students are. This is not something we have to do very often. She says, "It will no doubt be observed that in the course of these conversations, remarks are often introduced which appear much too acute for the young pupils by whom they are supposed to be made. Of this fault the author is fully aware, but in order to avoid it, it would have been necessary either to omit a variety of useful illustrations or to submit to such minute explanations and frequent repetitions as would have rendered the work much less suited to its purpose. In writing these pages, the author was more than once checked on her progress by the apprehension that such an attempt might be considered by some either as unsuited to the ordinary pursuits of her sex or ill-justified by her own recent and imperfect knowledge of the subject. But on the one hand, she felt encouraged by the establishment of those public institutions open to both sexes for the dissemination of philosophical knowledge, which clearly prove that the general opinion no longer excludes women from an acquaintance with the elements of science. And on the other, she flattered herself that whilst the impressions made upon her mind by the wonders of nature studied in this new point of view were still fresh and strong, she might perhaps succeed the better in communicating to others the sentiments she herself had experienced. Now, the friend with whom she conversed on the subject of chemistry was almost certainly her husband, Alexander Marseille. As mentioned before, some of his private notebooks still survive and are kept in the Bibliothèque de Geneva. They have recently been analysed from the perspective of Alexander's contribution to the Conversations on Chemistry by Dreyfus and Sigrist. They report on a particular entry written on December the 7th, 1807, at the completion of the printing of Conversations on Chemistry, and I quote using their translation from the French. "It was during the winter of 1801-2, I believe, that the idea for the book first came to my wife. We had often talked chemistry while travelling in France, and her curiosity was enough awakened for her to desire to watch me demonstrating the principal experiments. I wrote on cards the headings of small course of lectures, which she then read in the privacy of my own home, and more than once she alone was my audience. After each lecture, she produced a précis of what she had learnt, and I lent her my cards so that she could do this précis. Many years before, as her sister's teacher, she had begun the composition of a little course of physics in the form of dialogues, and the idea came to her to attempt the same thing on the elements of chemistry, an idea that I greatly encouraged. The resulting dialogues were modelled on the above-mentioned outline, and she had the opportunity one day of showing them to Mr. Pictet, who happened to be in London at the time. Mr. Pictet applauded and encouraged her to persist, which she did thereafter with much patience and perseverance. Soon I undertook the revision, and while the last chapters were being written, I began the correction of the first. These corrections proved extremely laborious for me. The style of the original was most haphazard, the tone often too much familiar, and there were from time to time contrasts too striking between the ingenuity of the teacher and the puerility of the remarks of her young pupils. Her courses were hardly completed, the punctuation virtually non-existent, and the details of my experiments often wrong. However, the chain of ideas and the plan of each dialogue were tolerably correct, and I was often surprised by their ingenuity. The author was at pains to go over her objections in good faith and the difficulties that are presenting themselves to her mind. And more often than not, I discovered my own answers, with which I was sometimes far from being satisfied. Of course, as happens during collaborations of this nature, and I note that my co-author for 2 books, Dr. James Keeler, is sitting in the audience, and indeed that James has just finished a major collaboration working on a new edition of Atkins' Physical Chemistry. So as happens during collaborations, squabbles sometimes arise. Alexander says, During the same period, the author attended from time to time the lectures given at the institution and here and there introduced some new passages, which then needed correction, after which my wife had to re-correct my corrections. And there was no end to our discussions. From this thankless, though at times amusing task, there resulted frequent little shocks of hurt pride and impatience. And my own irritable temperament provoked disputes, which often caused us to regret that we had ever begun our enterprise. All in all, however, the result of this shared endeavour of some 2 or 3 years has been an exchange of thinking, a multitude of points of contact which have been useful to both of us and whose effects will extend far beyond the memory of our little quarrels. Once all have been completed and recopied, Dr. Yellerley reread the work and indicated in pencil a number of corrections of style, which almost always tended to remove passages that were too familiar. After that, we placed, with Dr. Yellerley acting as our intermediary, the work in the hands of the bookseller, who had it examined by Arthur Aitken before giving it to the printers. Aitken's report being favourable, Longman & Co. proposed to cover all risks and share their profits with the author. Before printing, I again reread the work from cover to cover and corrected the numberless corrections and interpretations that had insinuated themselves since the previous revisions. Together, my wife and I corrected the galley proofs, and Aitken was kind enough to read the final proofs before going to press, making occasional useful corrections. Printing took 3 months. Actually, a letter still exists where London physician John Yellerley, who helped to edit the manuscripts of the Conversations, writes to Alexander Marseille. In one letter dated December the 23rd, 1803, Yellerley writes, "My dear sir, I now send you half a dozen of Mrs. M's books, which I have examined carefully, and in which I have noted such alterations as seem to me in any degree to improve her work. It is extremely difficult in a work of this kind to accommodate the language to the females for whose use it is intended, and to avoid, on the one hand, the familiarity which derogates from dignity of science and the abstruseness which has a tendency to make it forbidding. Upon the whole, I think it is better to elevate the minds of the young ladies too high than to depress them too low. And on that account, I have recommended you to omit remarks which, though they may be sufficiently natural from young ladies to their governess, are not in complete accordance with the philosophical views which they do easily comprehend. At the same time, however, whenever philosophical or technical expression has a corresponding familiar one, it is in general better to avoid it." In his journal, Alexander notes, I have forgotten to mention that the chapter on the vegetables and that on the animal realm has been compiled by my wife from different basic texts without any prior help from me. My lessons and the notes that I mentioned above not extending beyond the mineral domain. As for the preface, we both produced one without consultation. Then we combined them into one, of which mine furnished the greater part. The engravings are all the work of the author, apart from a few copied from other treatises. I arranged the apparatus, and she drew them from life. Lowry, this is the engraver, made some good corrections of perspective and rendered them much more perfect than we had flattered ourselves they were. These engravings gave us less trouble and as much amusement as any other part of the work. Jane Marseille's books first appeared anonymously. Her name didn't appear until the title page of Conversations on Chemistry, until the 12th edition, 25 years after its initial publication and after the death of her husband. 2 issues of the 12th edition appear, one anonymous and the other with Marseille's name appearing on the title page for the first time. Her second most popular book, Conversations in Natural Philosophy, with the same characters, Mrs. B, Emily and Caroline, had featured her name in the 6th edition the previous year, 1831, whereas up to that point it had simply stated by the author of Conversations on Political Economy and Conversations on Chemistry. As in her Conversations on Natural Philosophy, the Conversations on Chemistry are between the governess and Mrs. B and students Caroline and Emily. Mrs. B is thought to be based on Margaret Bryan, who had published a compendious system of astronomy in a course of familiar lectures in 1797 and lectures on natural philosophy in 1806. Having looked at the background behind the publication of the work, now let's have a look at the contents. So Conversations on Chemistry begin with Mrs. B introducing the subject to her two pupils. So Mrs. B, having now acquired some elementary notions of natural philosophy, I am going to propose to you another branch of science to which I am particularly anxious that you should devote a share of your attention. This is chemistry, which is so closely connected with natural philosophy that the study of the one must be incomplete without some knowledge of the other. For it is obvious that we can derive but a very imperfect idea of bodies from the study of the general laws by which they are governed if we remain totally ignorant of their intimate nature. Caroline says, to confess the truth, Mrs. B, I am not disposed to form a very favourable idea of chemistry, nor do I expect to derive much entertainment from it. I prefer those sciences that exhibit nature on a grand scale to those which are confined with the minutiae of petty details. Can the studies which we have lately pursued, the general properties of matter or the revolutions of the heavenly bodies, be compared to the mixing up of a few insignificant drugs? Mrs. B puts her back in her place a bit. She says, I rather imagine that your want of taste for chemistry proceeds from the very limited idea you entertain of its object. You confine the chemist's laboratory to the narrow precincts of the apothecary's shop, whilst it is subservient to an immense variety of other useful purposes. Besides, my dear, chemistry is by no means confined to works of art. Nature also has her laboratory, which is the universe, and there she is incessantly employed in chemical operations. You are surprised, Caroline, but I assure you that the most wonderful and the most interesting phenomena of nature are almost all of them produced by chemical powers. Without entering, therefore, into the minute details of practical chemistry, a woman may obtain such a knowledge of the science as will not only throw an interest to the common occurrences of life, but will enlarge the sphere of her ideas and render the contemplation of nature a source of delightful instruction. Caroline then concedes, well, if this is the case, I have certainly been much mistaken in the notions I have formed of chemistry. Now, Mrs. B's two pupils, Caroline and Emily, are quite different. Both very bright. Emily is extremely conscientious and always follows wherever her tutor leads. Caroline, on the other hand, is a little more brash, rather more questioning, not shy to get one over on her tutor, and always keen to try out the more exciting or dangerous experiments. Marseille's conversations start with a discussion of the simple bodies, what we would now call the elements. Following Lavoisier's list, in the first category comes heat and light. We shall study the list in greater detail shortly, but it is interesting to see how it changes through the different editions. For now, we shall simply note that Mrs. B instructed her pupils to learn the names of all the elements by heart for the next lesson. Caroline starts off the next lesson, conversation number 2 on light and heat. She says, we've learned the names by heart. We have learned by heart the names of all the simple bodies which you have enumerated, and we are now ready to enter on the examination of each of them successfully. You will begin, I suppose, with light. Mrs. B says, well, that will not detain us long. The nature of light, independent from heat, is so imperfectly known that we have very little more than conjectures respecting it. Emily says, but is it not possible to separate light from heat? I thought that they were only different degrees of the same thing. Mrs. B then says, they are certainly very intimately connected, yet it appears that they are distinct substances, as they can, under certain circumstances, be in a great measure separated. The most striking instance of this was pointed out by Dr. Herschel. This philosopher discovered that heat was less refrangible than light. For in separating the different coloured rays of light by a prism, as we did some time ago, he found that the greatest heat was beyond the spectrum, at a little distance from the red rays, which you may recollect are the least refrangible. Emily says, I should like to try that experiment. Mrs. B says, it is by no means an easy one. The heat of a ray of light refracted by a prism is so small that it requires a very delicate thermometer to distinguish the difference of the degree of heat within and without the spectrum. For in this experiment, the heat is not totally separated from the light, each coloured ray retaining a certain portion of it. The though the greatest part is not sufficiently refracted to fall within the spectrum. Emily then says, I suppose then that those coloured rays which are the least refrangible retain the greatest quantity of heat, and Mrs. B says they do so. Caroline then says, and this is rather nice, she says, perhaps the different degrees of heat which the 7 rays possess may in some unknown manner occasion their variety of colour. I have heard that melted metals change colour according to the different degree of heat to which they are exposed. Might not the colours of the spectrum be produced by a cause of the same kind? Do let us try if we can ascertain this, Mrs. B. I should like extremely to make some discovery in chemistry. Now this is all rather familiar, as I say, to some of the work that Madame Le Chatelet looked at earlier. But Mrs. B says, well, had we not better learn first what is already known? Surely you cannot seriously imagine that before you have acquired a single clear idea on chemistry, you can have any chance of discovering secrets that have eluded the penetration of those who have spent their whole lives in the study of that science. Caroline says, well, not much, to be sure, in the regular course of events, but a lucky chance sometimes happens. Didn't a child lead the way to the discovery of telescopes? And Mrs. B says, there are certainly a few instances of this kind, but believe me, it is infinitely wiser to follow a pursuit regularly than to trust to chance to your success. We should tell this to our students a lot of the time as well, I think. Emily then dutifully steers Caroline back to the topic at hand. But sadly, this little interjection from Caroline, professing her desire of chemical discovery, they're not present in the 3rd or later editions. In Volume 2, Mrs. B discusses compounds. She includes a nice description of nitrous oxide, a gas studied by Humphrey Davy before he came to the Royal Institution. Mrs. B, it remains for me only to mention another curious modification of oxygenated nitrogen, which has been distinguished by the name of gaseous oxide of nitrogen. It is but lately that this gas has been accurately examined, and its properties have been chiefly investigated by Mr. Davy. It has obtained also the name of exhilarating gas, from the very singular property which that gentleman has discovered in it of elevating the animal spirits when inhaled into the lungs to a degree sometimes resembling delirium or intoxication. Caroline says, is it respirable then? Mrs. B says, it can scarcely be called respirable, as it would not support life for any length of time, but it may be breathed for a few moments without any other effects than the singular exhilaration of spirits I have just mentioned. It affects different people, however, in very different manner. Some become violent, even outrageous. Others experience a languor attended with faintness, but most agree in opinion that the sensations it excites are extremely pleasant. Caroline then says, I think I should like to try it. How do you breathe it? Mrs. B then says, by collecting the gas in a bladder, to which a short tube with a stopcock is adapted. This is applied to the mouth with one hand, whilst the nostrils are kept closed with the other, that the common air may have no access. You then alternately inspire and expire the gas till you perceive its effects. But I cannot consent to your making the experiment, for the nerves are sometimes unpleasantly affected by it, and I would not run any risk of that kind. Emily then says, I should like, at least, to see somebody breathe it. Oops, what's happened to my... Oops. After trying some more experiments on the nitrous oxide, Mrs. B eventually says, you will see that the gas is now produced in great abundance. We shall collect a large quantity of it, and I dare say that we shall find some of the family who will be curious to make the experiment of respiring it. But sadly, she doesn't pick up on that later. It'll be interesting to see what happened. Interestingly, in one of the American editions, Caroline has quite a different view of trying nitrous oxide. She says, I, for one, have no inclination to get scientifically tipsy, as I well know that when in my sober senses my sayings and doings partake sufficiently of the extravagant, and I should expect, under the influence of your leaping, dancing and shouting gas, to exhibit the very perfection of the ridiculous. So it's a shame that they changed in that way, but there we go. We shall now look at, in details at the elements known to Mrs. B and how they changed in the different editions. So Caroline asks, But do not fire, air, earth and water consist, each of them, but of one kind of substance? Mrs. B says, no, my dear, they are every one of them but susceptible of being separated into various simple bodies. Instead of 4, chemists now reckon upwards of 40, there's now 118, 40 elementary substances. These we shall first examine separately and afterwards consider in their combinations with each other. She then lists the elements, and this is from the first edition. The list is similar to that listed by Lavoisier, notably in the fact that it begins with light and caloric, or heat. They thought that these were actually contained in different bodies. However, several newer elements are included that were unknown to Lavoisier, including tellurium, uranium, chromium, osmium, iridium, palladium and rhodium. And at this point, though, Caroline simply states, this is indeed a formidable list. But also included are substances that were suspected by Lavoisier and colleagues of not being elements, and these are the alkalis and the so-called alkaline earths. Only 2 alkalis are included, potash and soda. 10 earths were listed. The difference between the alkalis and the earths, by the way, is that the alkalis are soluble in water, whereas the earths do not dissolve in water to any appreciable extent. And some of these so-called earths are particularly interesting. Yttria was only recently discovered at this time, as was glucina. This latter element, or earth, was named after the sweet taste of its very poisonous salts. However, the name was criticised by one of the great mineralogists of the time, Klaproth, who said that this was not a unique property, since the salts of Yttria, named after a mineral found in the town of Ytterby in Sweden, were also sweet. When an element was eventually isolated from the glucina, it was for a while known as glucinium, but it later became beryllium, reflecting the precious stone in which it was found. However, one of the elements on this chart, Augustina, proved not to be an element. These earths, including the Augustina, were included in the 5th English edition of Lavoisier's Traité. In a note from the translator, Robert Kerr, he states that Tromsdorf, in the Saxon Beryl, thinks he has discovered a new earth, which he has called Augustine, from its salts being tasteless. This was later shown to be impure calcium phosphate. Now, sadly, I don't have a copy of the 2nd edition from 1807, and this seems to be quite rare, with only one copy listed on Copac, being that of the late historian J.R. Partington, and this is now housed in the John Rylands Library in Manchester. But by the time of the 3rd edition in 1809, huge developments had occurred, which meant that the entire list needed to be changed and reorganised. After the new list was given, Caroline then states, "Oh, what a formidable list! You will have much to do to explain it, Mrs. B, for I assure you that it is perfectly unintelligible to me, and I think rather puzzles than enlightens me." Mrs. B replies, "Do not let that alarm you, my dear. I hope that hereafter this classification will appear quite clear, and so far from perplexing you, will assist you in arranging your ideas." The elements were now shown split into their classes rather than all grouped together. No change in the first class, except now that electricity was also added to the heat and light. We shall see why this is the case shortly. Oxygen is still present as before. This is the only species in class 2. Class 3 are those bodies capable of uniting with oxygen and forming with it various compounds. Hydrogen is in a division in class 3 of all of its own. Then, in the list of bodies which unite with oxygen to form acids, in addition to nitrogen, carbon, sulfur and phosphorus, appears boracium, fluorium and muriatium. This is an error here dating back to Lavoisier, who had assumed that there is a substance, at the time not isolated, which combines with oxygen to form muriatic acid, what we would now call hydrochloric acid, and similarly one that combines with to form hydrofluoric acid, and more on these in a little bit. Then there is a section, metals, which unite with oxygen to form alkalis. Notice that ammonium features here. And then metals forming earth. Although the Augustina has now gone, several more have appeared. And you will be able to recognise most of them, except maybe the jargonium. Well, this is related to zirconium, which was first identified in the form of an earth, i.e. element combined with oxygen, by Klaproth in 1789, the same year he discovered uranium. He found the new earth in a precious stone from Ceylon called jargon of Ceylon, zircon, and later zircon. He writes, "I think myself justified in considering it as a new, distinct, simple earth before unknown, and at present I give it the name zircon earth, terra zirconia, until it may perhaps be found in another species of stone or possessed of other properties that may give rise to a more appropriate denomination." Well, as it turns out, it was soon found, in fact by himself, in another more common stone known as the hyacinth. But this gave him a dilemma: which stone should give its name to the earth? He writes, "The jargon has, indeed, already obtained that distinction, but ought it not to be transferred to the hyacinth, being a gem much older, longer known, and more esteemed? If so, the denomination hyacinth earth should then be adopted and substituted to that of zirconia or jargonia." As attractive as the name hyacinthium might sound, it was, of course, zirconium metal that was first isolated by Berzelius in 1824 by heating potassium metal with the salt of Klaproth's earth. In the 10th edition, and maybe the 9th, but I don't know because I don't have that one, the earths, after the earths are listed, Caroline says, "So then, instead of one single elementary earth, according to the simple science of the good old times, we now have nearly a dozen, and all of them are compounds. You must acknowledge, Mrs. B, that the philosophy of our ancestors had the advantage of simplicity." Mrs. B replies, "Well, simplicity has charms only so far as it accords with truth. I am far from supposing the present classification of simple bodies to be perfectly correct. On the contrary, the investigation and discoveries of the most celebrated chemists show us that occasional alterations already have been, and no doubt will continue to be required. But as long as every change brings us nearer to the truth, we have no cause to complain to their frequency. I do not mean, however, to depreciate the labours of our forefathers. We profit by their experience, both in avoiding their errors and in following their steps where they were in the right path. And it is no small advantage to be furnished with a handpost which indicates this is the right way and this is the wrong." Caroline then says, "People are very fond of expatiating on the wisdom and the experience of our ancestors, yet we must naturally be their superiors, since we have the advantage of all their accumulation of knowledge to follow and of error to avoid. And it would surely be much more rational to talk of the wisdom and experience of ourselves and of our posterity than that of our ancestors." Mrs. B answers, "I would admit that there is some truth in your observation, provided that you allow that it is not devoid of vanity. But we are wandering away from our classification of simple bodies, as are we. The huge changes necessary for this third edition were because of the discoveries made by Humphrey Davy at the Royal Institution." Mrs. B says, "Before we part, I must introduce to your acquaintance the curious metals which Sir Humphrey Davy has recently discovered. The history of these extraordinary bodies is yet so much in its infancy that I shall confine myself to a very short account of them. It is more important to point out to you the vast and apparently inexhaustible fields of research which has been thrown open to our view by Sir Humphrey Davy's memorable discoveries than to enter into a minute account of the particular bodies or experiments." Caroline says, "But I have heard that these discoveries, however splendid and extraordinary, are not very likely to prove of any general benefit to the world, as they are rather objects of curiosity than of use." Mrs. B says, "Well, such may be the illiberal conclusions of the ignorant and narrow-minded. But those who can duly estimate the advantages of enlarging the sphere of science must be convinced that the acquisition of every new fact, however unconnected it may at first appear with practical utility, must ultimately prove beneficial to mankind." Well, Davy's most important discoveries here took place on October the 6th, 1807, when, after failing to produce anything other than the splitting of water when applying his electric pile to aqueous solutions of the alkalis, he tried with pure molten potash, potassium hydroxide, heated on a platinum spoon. He was using the massive battery he had assembled at the Royal Institution in London with 24 plates of copper and zinc of 12 inches square, 100 plates of 6 inches and 150 of 4 inches square, arranged in horizontal troughs to contain the liquid. After tinkering with the conditions for a while, eventually a vivid action was soon observed to take place. And he writes in his paper announcing this discovery, "The potash began to fuse at both its points of electrization. There was a violent effervescence at the upper surface. At the lower or negative surface, there was no liberation of elastic fluid, but small globules having a high metallic luster and being precisely similar in visible character to quicksilver appeared, some of which burnt with explosion and bright flame as soon as they were formed, but others remained and were merely tarnished and finally covered by a white film which formed on their surfaces. These globules, numerous experiments soon showed to be the substance I was in search of, and a peculiar inflammable principle, the basis of potash." Within a few days, Davy had also, for the very first time, isolated the metal from soda, sodium hydroxide. Most remarkable was the action of these new elements with water, an experiment which still delights school children today. During the reaction, the potassium metal darts around on the surface of the water, giving out hydrogen gas, which helps produce the beautiful purple flame, and eventually all that is left behind is a solution of potassium hydroxide. Larger pieces react more vigorously, as Davy describes. He says, "The action of the basis of potash on water exposed to the atmosphere is connected with some beautiful phenomena. When it is thrown upon water or when it is brought into contact with a drop of water at common temperatures, it decomposes with a great violence. An instantaneous explosion is produced with brilliant flame, and a solution of pure potash is the result." Now, I know that there are a few people here that this is perhaps bringing back memories to them, since we had a little chemical demonstration in this very lecture theatre a while back. And it was just as described, in fact. Here is the picture. Yes, I think it was just as much as a shock to the chemist performing this experiment. He wasn't quite expecting that to happen. But anyway, Davy warns us. So calcium, magnesium, barium and strontium were finally isolated by Humphrey Davy in 1808, the year after he first prepared metallic potassium and sodium. The earths were trickier to isolate, as he could not use exactly the same method he used before. After a hint from Berzelius, he developed a method by passing the current from the giant battery at the Royal Institution through a slightly moistened mixture of mercury oxide and the appropriate earth, piled up on a plate made of platinum, which served as the positive electrode, with the negative electrode being inserted into a little globule of mercury recessed into the top of the mix. Unlike Berzelius, Davy managed to get sufficient quantities of the amalgams to be able to distill off the mercury and leave the new metals behind, although often still contaminated with mercury, especially in the case with calcium. Davy had to give names to the new metals, but the problem was another chemist had already used the name magnesium for the metallic form of manganese. So Davy felt that he had to come up with a different one. He writes, "These new substances will demand names, and on the same principles as I have named the basis of the fixed alkalis, potassium and sodium, I shall venture to denominate the metals from the alkaline earths barium, strontium, calcium and magnium. The last of these words is undoubtedly objectionable, but magnesium has been applied already to metallic manganese and would consequently have been an equivocal term." Well, these are the names that feature in Marseille's third edition. Curiously, except barium, which was not to feature until the next edition, the fourth, in 1813. In that edition, jargonium also disappears, by the way. However, by the time he published his book, Elements of Chemical Philosophy, in 1812, which was one of the first rare books I purchased and which we discussed in the first lecture, he has been persuaded to change his mind, writing in a footnote, "In my first paper on the decomposition of the earths, published in 1808, I called a metal from magnesia magnium, fearing lest if I called it magnesium, it should be confounded with the name formerly applied to manganese. The candid criticisms of some of my philosophical friends have induced me to apply the termination in the usual manner." But despite the fact that Davy changed his mind, opting for magnesium, this name did not feature in Marseille's book until the 12th edition of 1832. Davy was unable to prepare samples of the other earths known at the time, but he suggested names for them nonetheless. He writes, "Had I been so fortunate as to have obtained more certain evidence on this subject and to have procured the metallic substances I was in search of, I should have proposed for them the names silicium, alumium, zirconium and glucium, All of these names appear, as he recommends, in Marseille's third edition of the Earths, even though they have not yet actually been formed. Now, David's name, aluminium, deserves some further comment. Whilst his name perhaps reflects better the metal's origin from the salt alum, this name did not exactly roll off the tongue. It really doesn't. Davy himself soon changed his proposed name to aluminum, and then finally to aluminium. For a while, both aluminium and what has become the American choice, aluminum, sorry, I'm going to have to get my head round this, were in common use on both sides of the Atlantic. Initially, it hardly mattered, since the element could only be prepared in tiny quantities. In fact, aluminium was initially so rare and expensive, even more so than gold, that Emperor Napoleon III had some cutlery made from this strikingly light metal to use at his state banquets. But when the element could finally be produced cheaply in larger quantities, it came to the attention of the general public, and its name was questioned. During the 1850s, the famous British author Charles Dickens used to oversee the production of a weekly magazine, Dickens' Household Words. In the issue dated December the 13th, 1856, there appeared an article, Aluminium, in which it was announced, in a short time we shall be in possession of a new metal which we need not be ashamed to announce itself as by a distinct name. After giving a brief history, including mentioning Lavoisier's brilliant insight into the probable existence of new metals and the alkalis and the earths, the author writes, "What do you think of a metal as white as silver, as unalterable as gold, as easily melted as copper, as tough as iron, which is malleable, ductile, and with this singular quality of being lighter than glass? Such a metal does exist, and that in considerable quantities on the surface of the earth. Where, from what distant regions does it come? There is no occasion to hunt far and wide, it is to be found everywhere, and consequently in the locality which you honour with your residence. More than that, you do not want for it within doors at home. You touch it, not exactly by direct and simple contact, several times in the day. The poorest of men tramples it under feet, and is possessed of at least a few samples of it. The metal, in fact, in the form of an oxide, is one of the main component elements of clay. And as clays enter into the composition of arable land and are the material on which the potter exerts his skill, every farmer is a sort of miner, and every broken potsherd is an ingot in its way. Our newfound metal is aluminium." After extolling the wonders and merits of this new metal, he says, "Henceforward respectable babies will be born with aluminium spoons in their mouths." And the authors come to the choice of a new name for this metal. It says, "A final word. If aluminium is hoping to replace either gold and silver or copper and tin, or to take its own place without replacing anything, it may do so in the arts and manufactures, but it can never in literature or popular speech, unless it be fitted with a new and better name. Aluminium, or as some write it, aluminum, is neither French nor English, but a fossilized part of Latin speech, about as suited to the mouths of the populace as an ichthyosaurus cutlet or a dinornis marrowbone." That's one of my favourite little quotations there. Well, it was not until 1990 that the International Union of Pure and Applied Chemistry, the body who officially decide on the names of the elements, decreed that the official name should be aluminium. Of course, this did little to change the by then entrenched American version, aluminum, which had officially been adopted by the American Chemical Society 35 years earlier. The final thing that we need to comment on is the Muriaticum listed in the third edition, which remains until the 10th edition from 1825. This was an old name for what we now call hydrochloric acid. Now, while solutions of this acid were known since the 15th century, it was not until the late 18th century that pure hydrogen chloride was isolated, when Joseph Priestley became intrigued by an observation of Cavendish, who mentions an elastic fluid which retains its elasticity as long as there is a barrier of common air between it and the water, but which immediately loses its elasticity as soon as it comes into contact with the water. So Priestley followed up these hints from Cavendish and found that if you heated up a concentrated solution of hydrochloric acid, eventually you can get out, by heating up sulfuric acid and salt, you could get out this gas, which was extremely soluble in water. And Priestley used the term marine acid since it came from sea salt, but others, including the French reformers, preferred the Latinized term muriatic acid. However, the problem was that they were not sure what the acid actually was. Lavoisier writes, although we have not yet been able either to compose or decompose this acid of sea salt, we cannot have the smallest doubt that it, like all other acids, is composed by the union of oxygen with an acidifiable base. This assertion was based on Lavoisier's idea that oxygen was present in all acids, since, for example, it reacts with sulfur and water to form sulfuric acid, or with phosphorus and water to give phosphoric acid. Sadly, though, on this occasion, he was proved to be wrong, as he was with his assertion that muriatic could be made to combine with even more oxygen to form the toxic gas first isolated by Chatelet. So Chatelet, the Swedish chemist that we met yesterday, gave the first account of chlorine gas in his classic paper on manganese from 1774, where he describes how after heating the mineral pyrolusite, this is manganese dioxide, with muriatic acid, hydrochloric acid, an effervescence ensued with the smell of aqua regia. While Chatelet, in his usual meticulous manner, goes on to prepare and study larger quantities of the yellow gas enclosed in bladders or glass vessels. He describes the gas as a very sensible, pungent smell, highly oppressive to the lungs, and details its reactions, including how it bleaches coloured papers and flowers, and how it combines with metals, even with gold. Chatelet uses the phlogiston theory to describe how the chlorine is produced, saying that the manganese acquires a strong attraction for the phlogiston and removes it from the acid. He therefore refers to chlorine gas as dephlogisticated acid of salt. Well, of course, the French reformers reinterpreted the formation of chlorine in terms of their new oxygen theory. Rather than the hydrochloric acid losing its phlogiston, it gained oxygen to form chlorine. So Fourcroy writes about the reaction in 1786 and translated into English 2 years later. It is known that this production of a peculiar gas is due to the transition of the base of pure air, or the oxygenous principle of the calx of manganese, into the muriatic acid. Now, in modern terms, we would now say that the pyrolusite, the manganese dioxide, is an oxidizing agent, and that it oxidizes the negatively charged chloride ions present in hydrochloric acid to form the neutral chlorine atoms, which in pairs make up the chlorine gas. Rather than simply adding oxygen to the hydrochloric acid, the oxygen from the pyrolusite ultimately forms water with the hydrogen from the hydrochloric acid, and the net result is the transferal of negatively charged electrons from the chloride ions to the manganese. However, it is in the new nomenclature of the French, chlorine gas was called oxygenated muriatic acid. So for Lavoisier and his colleagues, at the very heart of both chlorine gas and hydrogen chloride was an unknown principle. As sulfur and phosphorus combine with oxygen and the overlooked water to form sulfuric and phosphoric acids, so this unknown principle combined with oxygen to form muriatic acid. The French chemists name this unknown substance muriatic base or muriatic radical, deriving the name after the example of Mr. Bergman and Mr. Morveau from the Latin word muria, which was anciently used to signify sea salt. Even though he did not know exactly what it was, Lavoisier included this muriatic radical in his list of the then known elements, and this is what gave this is what gave rise to the Muriaticum in Marseille's list. But just 2 years after his preparation of the alkaline earth metals that we saw, Davy published his papers on the nature of what was still then known as oxygenated muriatic acid. He tried every means possible to extract the oxygen out of both dry hydrogen chloride and out of dry chlorine gas. But Davy found that pure charcoal, usually very good at extracting oxygen and forming its gaseous oxides, even when ignited to whiteness in dry chlorine or hydrogen chloride gas, produced no change. Since chlorine gas so readily oxidizes other species, Davy was surprised by this result and wrote in 1810, "This experiment, which I have several times repeated, led me to doubt the existence of oxygen in that substance, which has been supposed to contain it above all others in a loose and active state." Davy resolved to make a more rigorous investigation than they had hitherto attempted for the detection of the missing oxygen. And after an extensive series of experiments heating various substances, including his newly discovered metal potassium, in either hydrogen chloride or in chlorine gas, Davy correctly concludes that any oxygen that is ever evolved is formed from any water present, and that the idea of existence of water in muriatic acid gas is hypothetical, depending on an assumption which has not yet been proved, the existence of oxygen in oxymuriatic acid. Interestingly, Davy begins his paper with a brief history of chlorine gas, writing the illustrious discoverer of oxymuriatic acid gas considered it as muriatic acid free from hydrogen, and the common muriatic acid as a compound of hydrogen and oxygen, oxymuriatic acid. And on this theory, he denominated oxymuriatic acid dephlogisticated muriatic acid. As we saw in the previous lecture, hydrogen was taken by some chemists to be pure phlogiston itself. And if we interpret Shaler's results in this way, dephlogisticated muriatic acid would be dehydrogenated hydrogen chloride, i.e. chlorine. Now, although Shaler probably didn't think of his discovery in this way, Davy seemed to think that he did, and is the correct explanation for the formation of chlorine. Davy does not offer a new name for this substance at this point, simply writing, "It is needless to take up the time of the learned society by dwelling on the imperfection of modern nomenclature." However, he does soon. In his next paper on the subject, read to the Royal Society and published the following year, he presents numerous experiments to show that chlorine is an element with similar properties to oxygen, and with a clear argument that the name should be changed. Davy eventually proposes a neutral name for this. He says, after consulting some of the most eminent chemical philosophers in this country, it has been judged most proper to suggest a name founded upon it of its obvious and characteristic properties, its colour, and to call it chlorine, or chloric gas. This is simply from the Greek, meaning greeny yellow, the colour of pure chlorine gas. And it took a few years for the conclusions of Davy's researches to be accepted, but eventually they were. And it was Davy's name chlorine that inspired the names of the other elements in the group from the periodic table that collectively became known as the halogens, and a very appropriate name for what means salt formers. Curiously, though, the next of these to be discovered was the last of the non-radioactive members of the element to be isolated in its elemental form, and this was the element fluorine. In the third edition of Marseille's work, there is a form of this, fluorium. And hydrofluoric acid had been known for some time. Indeed, Shaler gave a very detailed account of it. And once again, it was thought that there was a basis behind this that reacted with oxygen to form this acid, and that was what was appearing there. But as with earlier thoughts on muriatic acid, this is hydrochloric acid, Lavoisier believed then that fluoric acid was also composed of the unknown element combined with oxygen. And as soon as Davy had reported that muriatic acid did not contain oxygen, proposing instead that it was made of just hydrogen and the element he named chlorine, well, Ampere, who is now better known for his electrical discoveries, pointed out similarities between the two acids in a letter to Davy dated November the 1st, 1810. In a letter the following year, Ampere wrote again, suggesting that fluoric acid might be also oxygen-free and consists only of hydrogen and as yet an unknown unisolated element. And he wrote that he will call this new element fluorine by analogy with Davy's chlorine. Now, but in his second letter then, this is just where we're going to be finishing here, in his second letter dated August the 25th, 1812, where Ampere proposes the name of fluorine for the element that had yet to be isolated, right at the end of his letter, he makes a casual remark that was to change the course of science forever. In the final paragraph, Ampere asks Davy if he had heard about the highly explosive oil newly discovered in Paris and composed of just nitrogen and chlorine. He warns that a violent explosion of this highly unstable compound had cost its discoverer an eye and a finger. Curiously, David did not reply to this letter until 6 months later. He then wrote, "Sir, till this moment I had no opportunity of replying to your obliging letter. The fulminating oil which you mentioned roused my curiosity and nearly deprived me of an eye. After some months' confinement, I am well again." Well, although he didn't have time to reply to Ampere, Davy did manage to compose a paper on this new substance. He said to caution the English chemists against the oil. In the paper where he announces his findings, he had an explosion whilst trying to collect a considerable quantity of the oil. However, he was injured during a separate experiment where the gases were formed during the violent decomposition of the compound. He was heating a globule of the oil under water when suddenly a violent flash of light was perceived and a sharp retort, and the tube and glass were broken into small fragments, and I received a severe wound in the transparent cornea of the eye, which obliges me to make this communication by an amanuensis. He adds, "This experiment proves what extreme caution is necessary in operating on this substance, for the quantity I used was scarcely as large as a grain of mustard seed. Now, as reported, the accident meant Davy needed assistance to write his papers and employed a young former bookbinder. And this bookbinder was a young lad named Michael Faraday. Faraday later gave an account of how he got started in chemistry as a lad. He says, "I entered the shop of a bookseller and bookbinder at the age of 13 in the year 1804, remained there 8 years, and during the chief part of the time bound books. Now it was in those books, in the hours after work, that I found the beginning of my philosophy. There were two that especially helped me, the Encyclopaedia Britannica, from which I gained my first notions of electricity, and Mrs. Marcy's Conversations on Chemistry, which gave me my foundation in science. Do not suppose that I was a very deep thinker or was marked as a precocious person. I was a very lively imaginative person and could believe in the Arabian Nights as easily as in the Encyclopedia. But facts were important to me and saved me. I could trust a fact and always cross-examined an exertion. So when I questioned Mrs. Marcy's little book by such experiments as I could find means to perform, and found it true to the facts as I could understand them, I felt I had got hold of an anchor in chemical knowledge and clung fast to it. Hence my deep veneration for Mrs. Marcy, first as one who had conferred great personal good and pleasure on me, and then as one able to convey the truth and principle of those boundless fields of knowledge which concern natural things to the young, untaught and inquiring mind. You may imagine my delight when I came to know Mrs. Marcy personally, how often I cast my thoughts backwards, delighting to connect the past and the present, and how often, when sending a paper to her as a thank offering, I thought of my first instructress, and such like thoughts will remain with me." Now, the Royal Institution has in its amazing archives a letter from Jane Marcy to Faraday. She writes, it is dated 2nd of May 1846, and she writes, "Dear Mr. Faraday, could you give me permission to attend your lecture this morning? It is the only time I should be able to do so before I leave England, and I should be very sorry not to hear you once more before I go. At my time of life, return is so uncertain. Dear Mr. Faraday, very truly yours, J. Marset." Well, despite her uncertainty of whether she would actually make it back, the old girl had another 12 years in her after this, and she published the new edition, the 15th in 1846, and her last, the 16th, in 1853. But the esteem with which Faraday held Jane Marcy is evident in the reply to the letter, which is also still preserved. Faraday replies, "Dear friend, your request is an honour and most grateful to me, but do not come unless you feel quite able. I do not send you a ticket because I wish you to understand that on mentioning your name, you and a friend with you shall always pass here. I have so given order. Ever truly yours, Michael Faraday." Now, I hope I've been able in these 3 lectures to get across some of the excitement that I have for both chemistry and the dusty old books on chemistry. I've talked about the excitement I experienced on buying my first book by Davy on arriving in Cambridge before I'd even matriculated as an undergraduate. I've talked of the joy, amazement and privilege as an undergraduate of being able to go to the rare books room in the university library to look at some of their precious tomes. And I've mentioned the same excitement that I had on my first visit to the British Library and being handed copies of items that I'd only read about before. But there was one other moment in my life when I found this intense excitement when my worlds of chemistry and book collecting collided. And this was during the work with the Royal Institution preparing the Christmas lectures. This was a huge honour to be standing on the same space giving the lectures that Faraday had started so long ago. But I didn't mention so far exactly how Davy found out about this young bookbinder who had learned his chemistry from Mrs. Marcy. Like Jeremiah Joyce, and like Alexander and Jane Marcy, they, and like countless others, the young Faraday also attended the incredible lectures by Humphrey Davy at the Royal Institution. However, this young lad sat highly attentive to Davy's every word, and he made copious notes and then later wrote up these accounts of the lectures. After binding them, and after all he was a professional bookbinder, he then presented the book to Humphrey Davy. And it was this book of handwritten notes by Faraday that so impressed Davy that he gave him a job at the Royal Institution where he needed help after the accident. And of course, this then started his career as one of the most famous scientists we've ever had. Now, I'm absolutely thrilled that Professor Frank James from the Royal Institution has been able to bring this down for you today to see, and that's waiting outside. On that note, thank you very much. Thank you. I didn't realise I bent over.
Peter Wothers, I think I would like to say on behalf of all of us that that was an absolute tour de force. I feel quite scientifically tipsy, I say, with that wonderful conclusion to such an inspiring series of lectures. You have laid a sort of breadcrumb trail through that to this evening's finale, especially for us on International Women's Day, and so deeply showing your skill as a teacher, as a book collector, as a historian, and as a scientist. And just like the rather formidable Mrs. B, showed us how your chemical texts are a source of delight and instruction. I'm absolutely thrilled that you have been a 110th Sandars lecturer. I know that we're slightly over time, but it would be a real shame, given the quality of what we've heard, not to have time for a couple of questions before we go outside for something sparkly to drink. Would you be willing to take a couple of questions? Great, thanks. We've got two hands up already. Perhaps I'll go to... I cannot throw this that far. I know what's expected of me now, but I think it would cause a problem. Thank you.
Oh dear, I was dreading this.
No, Peter, that was super. Just one thing. Davy did have a practical use for sodium and potassium, and that was he suggested to the Navy that they should fill their guns with sodium and potassium and lob them at French ships. It strikes me as one of those ideas that is more dangerous to the user than the recipient.
Well, thank you very much. Thank you.
I think there's just a question in front of you as well.
So this is a very quick question, and it does refer to the young ladies who might have read this book. So Mrs. Marseille's book went through many editions on either side of the Atlantic during the period when ladies' academies, to turn them into governesses, were taking off in large numbers. When there was Charlotte Bronte going off to learn. Is there any evidence that they bought large numbers of copies?
Yes and no. Huge numbers of copies, not bought from Mrs. Marseille. These were all illegal, pirated copies from America. And so actually, in fact, there were numerous different publishers there producing these things because there weren't the same copyright laws in America at the time. But absolutely, these actually were used in schools, in ladies' academies, and there's direct evidence for that, yes.
Thank you.
Have we got one final question? So perhaps I can have the chair's privilege and ask you, after that incredible introduction over 3 evenings to your own collection, if one of your experiments went off in your own room, which is the text you're going to rescue and hold with you?
I don't know. I mean, yes, I do sometimes wonder about that. Yes. No, I'm really, no, I don't know. Yes.
Like any good book collector, all of those are equally precious. So,
yes, exactly.
We would love you to stay and join us for a glass of wine with celebration with Dr. Peter Wothers and for the Sandars Lectures of 2017-18. But before we do so, can we please show our appreciation most warmly?